Gradient of a curve and rate of change. The gradient or steepness of a curve varies. Now, whenever we talk about gradient, we might think about the general equation of a straight line, y equals mx plus c, where the gradient tells us how steep or shallow the line is and whether it slopes up or whether it slopes down. So whenever we talk about a gradient of a curve, you might be thinking, well, how can a straight line be part of a curve? And the reason for that, or the way we get around that in maths, is that we talk about the gradient of the tangent of a curve. So here we've got a curve, and we've drawn on certain tangent lines. Now, thinking back to circles, if we draw a circle, a tangent line is a line that crosses it at just one point, and it formed a perpendicular with the radius. So that's what a tangent was, and it's the same with a curve. So the tangent line cuts the curve at one point and would be perpendicular to some radius. The gradient at A, so we can see that it's sloping upwards, so it's going to be a positive gradient. The gradient at B, so it's a horizontal line, so there's no rise, so it's going to be 0. C has a negative gradient, it's sloping down. D is a gradient of 0, and E is sloping up, so it's a positive gradient as well. So to find the gradient of a curve, we need to draw a tangent to the curve and calculate the gradient of the tangent using our straight line gradient calculation. Now, if you remember that, if we had 2 points, x1, y1, and x2, y2, the gradient, which is still represented by the letter m, is y2 minus y1 over x2 minus x1, and we sometimes talked about the rise over the run. So that's how we'd work that out. So the gradient of a point on a curve is interpreted as the instantaneous rate of change at that particular point. So for example, in a velocity time graph, the gradient gives the acceleration, which is the rate of change of velocity. So the gradient at a point on a curve is the instantaneous rate of change. So the instantaneous rate of change of this graph at A is a positive instantaneous, and we could work out the value, and that would give us the rate of change at that point. We'd have a different rate of change at B, it would be 0. At C, we'd have a negative instantaneous rate of change, and then D would be 0, and E would be a positive. So example 8, calculate the gradient at the time t equals 5. So this is a velocity time graph, and when t equals 5, we've got the point here, but we want to draw the tangent to that, so we need to draw a straight line passing through that point, and that looks pretty good. So what we need to do is find 2 points that are exactly on that line, and then work out the value of the gradient. So here's one here at 6, 6, and the one at 5, 4 looks pretty good as well, so I'm going to use that. So the gradient is y2 minus y1 over x2 minus x1, which is 6 take away 4. So I'm using the y coordinates there for the 6 and the 4, and we're dividing that by 6 take away 5, which are the x coordinates. So 6 take away 4 is 2, 6 take away 5 is 1, so that means the gradient is 2. And to interpret that would mean that the rate of change of velocity is 2, which means that each second at that point the velocity would be increasing by 2, and the rate of increase of velocity is acceleration, so that means the acceleration would be 2. But what we know is, because it's a positive, that it's increasing as well. So the rate of change of velocity is 2, which is an increase, and that for this example the implication is that there is an acceleration taking place of 2. We may be asked to find the gradient of a curve, or a chord to a curve, sorry, and a chord cuts 2 places. So again, if we think back to a circle, so a chord is any line that cuts through it at 2 different places. So to find the gradient of a chord to a curve, so the chord would have to cut the curve at 2 different places, we'd need to know the points of intersection, and if we knew them, so we would have this coordinate would be x1, y1, and this would be x2, y2, and then we can use the gradient equation to work that out. So calculate the gradient of the chord between 4 and 8 seconds. So we need to draw the chord connecting the curve at 4 and 8 seconds. So that will be passing through this point and this point. And we have the coordinates of 4, 1 and 8, 4.5. So m is y2 minus y1 over x2 minus x1, which is 4.5 minus 1 over 8 minus 4, which is 3.5 over 4, which is 7 over 8, or 0.875. And what this tells us is that the average acceleration, because it's a velocity time graph and it's increasing, the average acceleration is 0.875 meters per squared second between 4 and 8 seconds. So it's the average acceleration. Example 10, the graph shows 90 minutes of an airplane's flight. Calculate the gradient of the chord between 20 and 25 minutes. So what we need to do is mark on our 20 and 45 minutes. 20 minutes is here, 45 is there. Let's draw the chord between those 2 points. And label on the coordinates. So the coordinate of the first one was 20 and 36,000, and the next one was 45, 28,000. So the gradient is y2 minus y1 over x2 minus x1, which is 36,000 minus 28,000 over 20 minus 45, which is 8,000 over minus 25, which is minus 320. So what that tells us in part B is that the altitude is dropping by 320 meters per minute. Feet per minute. So because it was a negative gradient, that means the altitude is decreasing. And even by looking at the graph, we can see that the graph is generally sloping down the way. So that means the altitude is decreasing. Next, calculate the gradient of the chord for the next 45 minutes. So for the next 45 minutes, we have to get to 90. So there's 90. Its coordinate is 90 and 8,000. So if we were to work out the gradient using the formula above, it's going to be 28,000 minus 8,000 over 45 minus 90, which is 20,000 over 45, which works out to be, minus 45, which works out to be minus 444.4 feet per minute. So the gradient is minus 444.4, so which means it's still dropping, and it's dropping quicker. So there's a more rapid decrease of height.